Põe um assim cheio, isso, assim, e daí não sujeira. Isso, e daí não fica não. Deixa aí, deixa aí. Tá bom. So welcome everyone to today's seminar. Today we have Bahar Bidaran from the University of Granada in Spain. Just a second. So Bahar is originally from Tehran in Iran. She did her bachelor's in physics and graduated in 2014, and a master's in astronomy in Al-Azhar University. She then did her PhD at the Heidelberg University in 2021 in Germany. And now she's at her first postdoc at the University of Granada, and she's part of the cavity collaboration, mainly focusing on the formation and evolution of low-mass galaxies, the dwarf galaxies, in high and low-density environments. Thank you so much, Bahar, for accepting our invitation. The floor is yours when you're ready.
Thank you. Hello, everyone. And thank you also for inviting me and providing me this opportunity to present my work here. Today, I'm going to present the work I did during my PhD. And of course, this was not like a one-person task. It was a collaboration with a team. And here I'm providing the name of some of my collaborators. And as the title suggests, today I'm going to talk about pre-processing in dwarf galaxies. So first, I will give some reasons and some explanations as a motivation of this work, that why we should care about pre-processing in dwarf galaxies. Then I introduce you a sample of pre-processed dwarfs in the Virgo cluster, and later I will explain the results that we have obtained and try to put them in the general context of star galaxy formation and evolution that we know. Okay, dwarf galaxies. Low mass galaxies, less than 10 to the 9, 10 to the 9.5 solar masses, one of the most abundant type of galaxies in the universe. And these are important features, important galaxies, because I believe they hold keys to the answer of many questions we have about formation and evolution of the galaxies. For instance, they are providing these extreme rare, extreme star forming environments, low metallicity, low density, so they could shed light on the details of star formation processes in the galaxies. They have low mass, so this makes them prone to the environmental and to the internal feedback. So this is also an important aspect of understanding galaxy evolution in different phases. And also they are important entities to solve some of the cosmological tensions that we have between observations and simulations, for instance, the too big to fail problem and so on. But the term dwarf galaxy is a very general term, I believe, because this implies low mass galaxies, but then on the low mass end of the distribution, you have different type of galaxies with different characteristics, different evolutionary histories, and possibly different origins. You have tidal dwarfs, you have blue core dwarfs, you have ultra faint dwarf galaxies, early types, late types, compact galaxies, etc. And here I'm showing you 3 different examples. They are all called dwarf galaxies. They are all in our local group, but as you can see, they have different properties. They are not only in morphology, they are different, but also in terms of stellar population properties, star formation histories, they are in different stages. So the term dwarf galaxy and whatever results we get for dwarf galaxy, we cannot really generalize it to all types of dwarfs. And today, this talk explicitly is about early type dwarf galaxies. So early type dwarf galaxies are the most abundant type of galaxies in high density environments, like in clusters, in galaxy groups. If you want to know how they look like, then I shall present you one of the most famous cases in our own local group, NGC 205. This is a satellite of Andromeda Galaxy. You can see the early type morphology of this galaxy. So the smooth light distribution that these galaxies usually have, they are dominated by red light, indicating that the stellar population properties in this stellar population in these galaxies is very old. They have low star formation rate, if any. And recent studies also show the possibility of the presence of some substructures like disks, spiral arms, bars in this type of galaxy. It is still a big question for us that how this type of galaxies form. And there are different scenarios proposing different possibilities, but two of them have gained further attention. The first one is based on the lambda CDM, hierarchical structure formation. So based on this scenario, we believe that at least a subpopulation of present-day early type dwarf galaxies are those primordial galaxies that formed in the early universe but did not go through any mergers. And there are some observational evidence supporting this scenario. And the other one, which is more famous, more observational backup is there for it, is the transformation due to the environmental effects. So this scenario suggests that present-day early type dwarf galaxies that we see in clusters are actually remnants of late type star-forming galaxies that came to the cluster, came to the group, and transformed due to the environmental effects. I'm calling environmental effects every time, but what do I mean actually by that? In order to summarize and give you a picture of what I mean by environmental effect, I shall present this beautifully illustrated plot by Irie Chung. So here there are different environmental processes that a galaxy would experience going to a high density region like a cluster or group. So you may be familiar with some of them here. For instance, the ram pressure stripping is the most famous one of the most famous ones. It's the act of removing gas from the galaxy as it goes through the intercluster medium of a cluster or a galaxy group, intercluster or intergalactic medium. And it's because the intergalactic medium has higher density and the galaxy is moving with a certain velocity. The temperature is also higher, so it is easy for the gas to be removed from the galaxy. And when a galaxy loses its gas, it loses its ability to form new stars, right? Also, in high-density environments like clusters or groups, you have tidal forces, tidal interactions between different galaxies, like mergers, close flybys, and also tidal forces exerted by the host halo, like the cluster or the group, can also exert their own tidal forces. And also we have a starvation, thermal evaporation, etc. I'm not gonna go through the details here, but I want to emphasize that in any high density environment, galaxies can feel these processes. And it doesn't necessarily mean it's only the present day host halo that acts on the galaxy. It means that when you as a galaxy, you can come to the cluster individually or from a filament or as a member of a galaxy group. And it means that these environmental processes could affect you before coming to the present day cluster partially or completely. And this is what we call pre-processing. So the act of partially or completely transforming galaxies' properties due to the environmental effects before they come to the present day host halo. Okay, this is not just a speculation, right? So we have observational evidences supporting the correlation with the environment. Many studies talking about that. For instance, you may be familiar with the morphology density relation, saying that in the high density parts of clusters, like the core of the cluster, you have dwarf galaxies in general that have more of early type morphologies with low to zero star formation activity. And as you go to the outer skirts of the cluster, to field, to less dense regions, this morphology becomes more of the late type, and the star formation rate of the galaxies increases. Another piece of evidence suggesting the environmental role in quenching dwarf galaxies and affecting their properties is this work done by Galaxy et al. So you are looking at SDSS galaxies, different stellar masses on the x-axis and the quenched fraction on the y-axis. Here, galaxies are beamed based on their host halo mass. So galaxies that are in the pink trend are galaxies that are in the most dense host halo, like 10 to the 14 solar masses. This is similar to the Virgo condition. And as you can see, for low mass galaxies, this is not covering all the dwarf mass range, but this is like touching the high mass dwarfs part. You can see that like those dwarfs that are in high density environments on average have higher quench fraction compared to the galaxies that are in less dense environments of like a group, a small group, or the field. Another piece of evidence is a recent work by Romero Gomez. So here they are investigating the stellar population and star formation history of dwarf galaxies in the core and outer skirts of the Fornax cluster. Forget about the yellow and red profile here because these are massive galaxies, okay? So let's focus on the blue and the green profiles. These are dwarf galaxies from the STOMI Fornax survey. And here in this plot, you are looking at the cumulative mass fraction as a function of look-back time. It means that it tells you at different epochs of the universe, let's say 14 gigayear, which is the big assumed Big Bang time, or 10 gigayear, what fraction of present-day stellar mass has been formed inside the galaxy. Blue profiles are galaxies in the core of the Fornax, one of the highest density regions in our universe, at least in our local universe. And the light green are dwarfs in the outer skirts of Fornax, between 0.8 to 1 virial radius of the Fornax. And they are showing that dwarfs that are in the core of the Fornax on average form their stars earlier than those in the outer skirts. In another word, dwarf galaxies that are in the outer skirts of Fornax have been active forming new stars much recently compared to those that are in the core of the Fornax. This is another reflection of the environmental effect on evolution of the galaxies, because galaxies in the core of Fornax on average have been exposed to the environmental effect for much longer time than those that they are in the outer skirts. Okay, how can we see this correlation with the stellar population properties? Because the stellar population properties are the fossil records of the evolution trajectory of the galaxies. And this is one of the studies from among many different studies that are available in the literature. This is the work done by Smith et al. In 2009. You are here looking at dwarf galaxies in the Coma cluster. Here you have the age, metallicity, and alpha over Fe, which is the chemical enrichment in the galaxies as a proxy of the chemical enrichment in the galaxies, as a function of projected distance to the center of the cluster. And in this study, they show that dwarf galaxies that are in the core of the Fornax are on average older, metal poorer, and more alpha enhanced as compared to those that are in the outer skirts of the Coma cluster. This is nice. So I think up to now, I have convinced you that the environment is the key, right, in quenching dwarfs. But this solution has also some problems. The first problem is that we also have found quenched dwarf galaxies with early type morphologies in the field, in the outer skirts of the clusters. The second problem is that these relations, most of them are when you want to define or quantify the environment of the galaxy, when many people use the projected distance to the center of the cluster, the local density. This is projection, right? And it's also suffering from the projection effect. So if you have a dwarf galaxy in the center, it can be actually in the center of the 3D structure of the cluster, or anywhere along the line of sight between you as an observer and the center of the cluster. So this increases the scatter that we see in the trends. And also another source of scatter is the pre-processing, which I just explained to you, right? So maybe some of these galaxies have been partially or completely affected by another environment before coming to the Coma cluster. And if we don't account for the pre-processing, then we are putting too much weight on the cluster's role in quenching dwarfs, and this is where our models and observations do not really match. So pre-processing is very important, but as an observer, it's very difficult to track a galaxy inside the cluster and understand what has happened to them before they come to the cluster. And many people try to solve this problem, and I think the concept of infall time and the phase space diagram is the key. So here on the left panel, you are looking at the Virgo cluster. Here, this is the plot by Siblesky et al. In 2017. You are looking at all the dwarf galaxies of the Virgo. They are color-coded based on different substructures that they have. And talking about that is beyond the scope of this talk, so I'm not going to go through the details of substructures here. But based on this map, they could plot or they could compute the number density map for the Virgo cluster. And as you can see, Virgo is not that neat a spheroidal cluster that we are all happy with, but it's rather under construction. It has some of these high density patches here and there. So it's not a really easy case, right? But the idea is that we want to know the trajectory of the galaxies inside this cluster. So at the same time that Sigleska was working on the number density map of the Virgo, introduced the schematic trajectory of the galaxies on the phase space diagram. And let's match these two together and let's understand what does this phase space diagram can tell us. So position of your galaxy coming to the cluster changes on the phase space diagram, the longer the time it spends inside the cluster. So at different stages of infall to the cluster, position of the galaxy changes on the phase space diagram. Let's assume you have a galaxy in point A. The first time it's going to fall into the cluster, so somewhere here. So from point A to point B, which is the first phase of infall, going from point A to the first pericenter passage into core, the position of the galaxy on the phase space diagram changes from point A to point B. So if you find a galaxy in point B and just the projection, you would assume this galaxy is in the center of the cluster and has been there for a long time, so it should be affected by environment, right? But it's not actually true. If you put the position of that galaxy on the phase space diagram, you will see that it's here in the first pericenter passage. And in fact, it has been inside the cluster for 2 to 3 gigayears, or even less than that. Then the galaxy doesn't stop there. The galaxy, depending on the kinetic energy, initial kinetic energy it had, and the trajectory it went through inside the cluster, may end up in point C, which is the first pericenter passage, and we call these galaxies backsplash galaxies. So if you just look at the distribution, you would say, oh, this galaxy is out of the cluster, so it should not be affected by the environment, which in reality, it has been affected by the environment, and it's just there because it has gone through the first infall phase inside the cluster. And this back and forth continues until, depending on the kinetic energy of your galaxy, it ends up in the realized zone, which is somewhere near the center of the cluster. So phase space is the key, right? So you can maybe quantify the exposure time of the galaxy inside the cluster based on its position on the phase space diagram. And this has been the topic of work for many, many people. Here I'm showing you the result of Pasquale et al. In 2019. So here what they did is that they went to the simulations, because from simulations you have the average infall time of the galaxies, right? And they quantified different zones. They defined and quantified different zones of the phase space diagram here. So from zone 8 to zone 1, and different zones have different average infall times that are listed here. So it means that if you go to a galaxy, plot the distribution of the galaxies on the phase space diagram, and you find the galaxy in zone number 5, let's say, according to their results, on average, this galaxy has spent 3.3 gigayears inside that cluster. Of course, this is a statistical method. It's only working for a large sample of galaxies, etc. But this is the first step for us observers. So now we can quantify the exposure time. Yay. Is there any correlation? Yes. Many studies are working on this, and here I should go back to the Galaxy et al. In 2021. Here, this time, they have quantified the galaxies based on their average infall time to their clusters, to their groups, to their host halos. Recent infallers have been exposed to their present-day host halo environment for less than 2.5 gigayears, and ancient infallers for more than 2.5 gigayears. And they showed that recent infallers are on average younger, metal poorer, and less alpha enhanced compared to the ancient infallers. And there are more studies showing different correlations. If you are interested, please go and check them. Okay, Again, motivated by the concept of phasal space diagram, Lisker et al. In 2018 went back to the Virgo cluster and plotted the distribution of all of the galaxies, not just dwarfs, all of the galaxies of Virgo on the phasal space diagram. On the left-hand panel, I'm showing 6 different panels because they beamed their galaxies based on the absolute R-band magnitude, which is a proxy also for the stellar mass. And they found out that in this particular band between -17 to -18, there is this suspicious grouping of galaxies, 9 galaxies in this particular zone of the phasal space diagram. And this accumulation, this gathering means that all of these galaxies have the same distance and the same velocity inside the Virgo cluster. And this was suspicious. So they went to the embodied simulations and they found out that if you have a galaxy group falling into the Virgo 2 to 3 gigayears ago along the line of sight, then here I'm showing the distribution of the galaxies inside that group. The distribution of the galaxies inside that group 2 to 3 gigayears after the infall mimics similar distribution that they saw in the observed phasal space diagram there. This is what I told you is very short summary of a very detailed analysis that they did. So if you are interested, please go and check their work. But this is how my sample, the sample I spent my entire PhD with, was born. So 9 dwarf galaxies, all with the same infall time to the Virgo cluster. Here on the top, I'm showing their pictures. They have similar stellar masses. All of them are early type dwarf galaxies. And also based on the a statistical method of Pasquali, we could also again confirm the same average infall time that the simulations gave us 2 to 3 gigayears ago. And here on the right-hand panel, I'm showing you the distribution of them inside the Virgo. So they are in the outer skirts of the Virgo, and they are distributed around the center, if you can find a center for Virgo. And this is because the accretion of group was along the line of sight. So we went to the MUSE, perfect instrument for analyzing dwarf galaxies. We observed all of these 9 dwarfs. We did the data reduction ourselves, and we did some analysis on their kinematics, which I'm not gonna cover this today in this talk. The results of the kinematics are published in Bidaran et al. 2020, but today I'm going to only focus on the stellar population properties because they are the key. They are the fossil record of what happened to the galaxies. So to derive the stellar population properties, we went to the MUSE cubes, we masked the foreground and background sources, unwanted sources. Then we used the Voronoi binning method to bin the data so that each spatial bin has a signal to noise of more than 100. For dwarf galaxies, this is amazing. And then because we had this good signal to noise, we could also go to the Lick indices and derive the stellar population properties of these galaxies using the Lick indices. Here I'm marking five Lick indices that we used in this study. So we have H beta, which is sensitive to the age. We have NGB and the composition of 3 different iron bands, which are also sensitive to the metallicity and chemical enrichment in the galaxies. So to derive the stellar population properties, age, metallicity, and alpha over Fe, we use the Lick indices based on the 4-step fitting routine, which was based on the Chi2 minimization approach. This is the method that we developed for this study. I'm not going to go through the details here again. If you are interested, we can discuss that later, or the details are in the papers mentioned here. Then again, as if you are familiar with the stellar population properties and fitting and driving these parameters, you know that we are very dependent on the stellar population models that we select. For this case, we use the MUSE stellar library. And this is like the assumptions and the initial parameters that we selected, the age range, the metallicity range, and the alpha over Fe. If you're familiar with this library, you know that MUSE has only models for 3 different values of alpha over Fe, which is 0, 0.2, and 0.4. But we know that dwarf galaxies can sometimes have very high alpha over Fe or very low alpha over Fe. And in order to minimize the systematics here, we extrapolated the models and expanded the range of alpha over Fe between -0.3 and 0.6. And also as a secondary method, in order to make sure the values we are getting make sense, and also in order to have the star formation histories, of these galaxies, we went to the full spectral fitting technique using the starlight, again based on the same stellar population model. Now let's go to the results. This plot is chaotic, I know, but please walk with me so you can understand what's happening here. So here in these three different panels, I'm showing the phasal space diagram from Pasquale et al. There are three different zones in each diagram, and different zone corresponds to different average infall time. So zone 1 is the average infall time less than 2 gigayears, zone 2 is between 2 to 5 gigayears, and zone 3 is more than 5 gigayears. Here I'm showing the galaxies, the 9 pre-processed candidates that we are working on with a square symbol, and also they are further marked with a green box. I'm comparing them with equally massive, and I have to emphasize equally massive. So whatever difference you see is not the difference of stellar mass, it's the difference of environment. Equally massive dwarf galaxies from the Coma cluster, denoted with circles, and Virgo cluster, denoted with a plus symbol. And all of the data points are color-coded based on their age, metallicity, and alpha over Fe. In terms of age, we didn't see any particular correlation between the age of the dwarfs and their average infall time, but what should catch your attention is that for our sample, 9 dwarfs, exactly similar accretion time to the Virgo cluster, but they have different ages, and this age is light-weighted, and it's the average over the galaxy because we wanted to compare statistically with other galaxies. So they have different ages, 2 to 11, same accretion time to the cluster. It's very unlikely that Virgo acts selectively on its infalled galaxies, right? So this could be the first hint of pre-processing in these galaxies. In terms of metallicity, we didn't see much difference, which is expected because we are looking at dwarf galaxies of the similar stellar mass range, so we don't expect to have drastically different metallicities. But alpha over Fe, we detected high alpha over Fe values in all the 9 dwarf galaxies that we investigated, the pre-processed sample compared to other dwarf galaxies in the Virgo with different infall time, to other dwarf galaxies in the Coma with different infall time. And this is important because let me remind you of these two different separated studies. That high alpha over Fe is expected in dwarfs, but if the dwarf is located in the center of the cluster, and that high alpha over Fe, not even that range, but higher alpha over Fe relatively, is expected for ancient infallers. Our galaxies are recent infallers in the outskirts of Virgo. So why they have higher alpha over Fe? To answer that question, we went deeper, and we first of all studied the stellar population properties maps because we have MUSE here. So here I'm showing you an example. This is one of the galaxies. As you can see in the center, it's dominated by younger stellar populations and metal richer, and in the outskirts, it's the older stellar population and metal poorer. And also at the same time, because we are also using the full spectral fitting, we defined two different beams, central and outer skirts. So central is up to 0.4 effective radius of each galaxy, and outer skirts is beyond 0.4 effective radius. And we beamed the MUSE data, and we ran the full spectral fitting. So on the top, we are looking at the light fraction as a function of look-back time for the central part of the galaxy. And in the bottom, we are looking at the same thing for the outer skirts of the galaxy. And we found out that for 6 out of 9 dwarfs in our sample, they have experienced this enhanced star formation activity at or after their accretion onto the cluster Virgo. So here the vertical dashed lines are the two estimates of the average infall time from the simulation, Lister et al., and from the statistical method of Pasquale. And we believe it's because these galaxies had some gas reservoir, and because they came to the cluster, so the density of the environment has changed, and they have felt this shock that has increased the surface density of the gas, particularly in the core of the galaxies, in the central part, which is the deepest part of the potential, right? And that has increased the pre-existing star formation activity or initiated a new episode. And because the duration of this episode is very short, it reflects itself as a high alpha over Fe value, which is also from light weighted. all of them are light-weighted, right? So it reflects itself as a high alpha over Fe that we have detected for 6 out of 9 galaxies in this case. So this is a clear case. This has been also investigated by simulation. So we know that this effect exists, that ramp pressure at the time of accretion to the cluster can give the shock to the galaxy and increase the density of the gas, remaining gas inside the galaxy. And this is a clear case of early processing inside the cluster. For the other 3 galaxies in our sample, we found out that both in the central part and in the outer skirts, there was no star formation activity at the time of accretion, meaning that all of these 3 galaxies have formed all of their stellar mass long time before they accretion to the cluster, and this is a clear case of pre-processing. And since the duration of star formation in the past in these galaxies was also short, it also reflects itself as a high alpha over Fe that we detected in these galaxies. Now that we hopefully have solved the mystery of high alpha over Fe, let's go deeper and see what we can get from the radial gradients of stellar populations in these galaxies. Because if you compare these 2 maps, you can see that there is a clear difference. In some of the galaxies, we had this positive age gradient. Some of them had this completely flat age gradient. So can we get some information from there as well? So here I'm comparing our galaxies. This work means our galaxies, circles denoted with circle data points, with dwarf galaxies from Virgo and Fornax. And I want to take this chance and to emphasize that the number of dwarf galaxies for which gradients of a stellar population has been reported in the literature is extremely trace. Like the time that I was doing this study, it was only reported for 50 dwarf galaxies. And if you are interested in this line of research, this is a huge opportunity to go and check the gradients of stellar populations in dwarfs, because I think they hold key answers to some of our questions about evolution of galaxies, dwarf galaxies. So here I'm comparing these 3 different samples, and this is the gradients of age as a function of sigma velocity dispersion, which is a proxy of the stellar mass in the galaxies. We went with the sigma because there are many studies showing that there are better correlations or more strong correlation between different parameters and sigma compared to stellar mass. And also to derive the stellar mass, you need to rely on the models and the assumptions of the models. It's not the direct measurement that you can get as you can get from the sigma. So we detected almost flat age gradient in the dwarfs, comparing to the general, compared to the other dwarfs that we had from the literature. Negative alpha over Fe gradient as a function of a stellar mass, and with a large scatter, the same almost negative gradient for the metallicity. I'm also showing the gradients of indices because indices are directly measured, so they are also not relied on the assumptions of the models. And we detected the same negative gradient in MGB, which is a tracer of metallicity and alpha over Fe. These are galaxies from 2 different clusters with 2 different conditions, and also the Virgo DEs that I'm showing here have different average infall times compared to our sample, but we don't see any correlation with the environment. So we don't see any correlation with the gradients of stellar population properties and the environment. But as I mentioned, this is based on very few dwarfs. So we need larger samples in order to confirm this. And let's compare this with more massive galaxies, early type galaxies. The upper 2 panels are a mess, especially in terms of metallicity. And this is because different studies use different methodologies in order to derive the stellar population properties, etc. And that results in really different values. And I'm showing this to emphasize on the method that we use and understanding the systematics that different methods can introduce to the results that we have. We can discuss this later if you are interested. But what was interesting to us at that time was that despite all these differences that we see in age and metallicity, but for alpha over Fe, all the studies seem to agree with each other. The scatter or like discrepancies is minimal there, and we could find, adding dwarf galaxies to this relation, we found a negative correlation with the gradients of alpha over Fe as a function of stellar mass or velocity dispersion here, meaning that for massive galaxies, because for massive galaxies, this value is around 0. So in massive galaxies, there is no gradient of alpha over Fe on average. And it is because, remember, alpha over Fe is a proxy of the duration of a star formation in a galaxy. And in massive galaxies, star formation is instantaneous, happens very fast, immediately, it doesn't leave time for the gradient of alpha over Fe to form, whereas in dwarfs, the star formation is more prolonged, and this is something that different studies have concluded. So it's more prolonged, and it is not only more prolonged, but it's more confined in the central part of the dwarfs, because that's where the potential is deeper. That's where dwarf is more capable of holding its gas to form more stars. And that's why you are looking at higher, at positive alpha over Fe for dwarf galaxies. Again, we need more dwarf galaxies to confirm these relations. And also, I want to present this plane, the famous mg over Fe versus Fe over H plane, which is one of my favorite tools. So you are all familiar with the alpha Ni and the distribution of the stars of Milky Way on this plane. We are using this in order to understand when and where and how the enrichment of the intergalactic medium was dominated by supernova type 1 or supernova type 2. It's a very important tool for people who are working with the resolved stellar populations. On the background, I'm plotting the stars from Milky Way and the average trend just for the ease of your eyes, because we cannot really compare here things. In the background, we have stars. In the foreground, we have light coming from different beams. So it's not really one-to-one comparison. But what is interesting here is the comparison between dwarfs. So here I'm plotting the average profile of 20 dwarf galaxies, similar stellar mass range than our sample in the dashed black line. And as you can see, it is rather a long trend going from 0.4-ish to minus 0.1-ish on the y-axis, which is mg over Fe. And I'm comparing the profile that we get for our pre-processed galaxies with different colors they have. And these are the different names of the galaxies, and each galaxy is presented properly. Here is the central part of the galaxy. So the difference we are looking at is not because of the signal to noise or anything. This is the central part. And as you go upward, you're going to the outer skirts. What is interesting here is the truncated profile of our pre-processed dwarfs compared to other dwarf galaxies in the Virgo. And this is because in the center, they have lower metallicity and also higher alpha over Fe. And as I explained earlier, the high alpha over Fe and lower metallicity for 6 of them is because of the early processing in the Virgo. For the other 3 of them is for them being pre-processed in a different environment or whatever reasons. But I wanted to show this plot because I think this is the time that we go back to this, and there's a lot of potential to this plane. Now that with upcoming observations, now finally we can do resolve the stellar populations in nearby galaxies beyond the local group. So maybe this is the time that we can reveal more secrets from, or more tools, we can construct more tools from this plane. So just to bring back your attention to this plane. And now this is the time for conclusion. So before I jump to the detailed conclusion, I just wanted to mention that this talk was about pre-processing. As an observer, finding pre-processed galaxies has always been a challenge because we cannot track the galaxies. But now with the infall time, and hopefully if I could convince you, combining the infall time information from the phase space diagram with the stellar population properties, particularly alpha over Fe, star formation histories in different parts of the galaxy, and the mg over Fe versus Fe over H, we can find them. We can find pre-processed galaxies. We can remove them from our general trends, or we can particularly focus on them. This is the 3 cases that we saw the drastic difference between our dwarfs and other dwarfs that are not really pre-processed inside the Virgo. Yeah, and then this is the detailed conclusion. I leave you with that, and I'm now happy to answer all of the questions. Thank you.
Thank you, Bahar. Do we have questions from the audience that you want to speak up, or shall I read it? Okay, if you have more questions, just to write it out. So, okay, I'm gonna start from the bottom. So number 5. So we have the students have written down the questions so that we can read them out loud. So considering the dwarfs which quenched before infall, how do you differentiate galaxies that quenched due to pre-processing from those that quenched simply due to starvation?
That's a good question, actually. So starvation is always counted as the effect of environment, because in the normal case, the galaxy should be linked to the fuel, the gas fuel line that fuels it for forming new stars, right? So starvation is usually linked with the environment. And in this study, we didn't go in detail to see what happened previously, because we use the statistical method for deriving the average infall time. Also, it was the embodied simulation suggesting it was part of a galaxy group. So we didn't go in detail to see what was the cause of the quenching. It could be starvation, it could be RAM pressure stripping in a different environment. It could be many things. And now that we are working in voids and in much less dense environments, we know that it's not just the starvation or the environment, but also it can reflect back on the halo assembly of the galaxies for quenching them. So at this stage, with these results, with this work, I cannot really say what quenched them, starvation or not a starvation, right? But hopefully in the future, we can find some diagnostics also for the starvation in the galaxy.
Thanks. Another one. Could your 9 dwarfs have gone through a blue compact dwarf phase?
Which phase?
Blue compact dwarf. Could they have been at some point blue compact dwarfs?
I don't think so. I don't think so, because I'm not really familiar with the details of the blue compact dwarfs, but these galaxies in terms of size are a bit more extended than the blue compact dwarfs. They have disk substructures, some of them have a spiral arms, some of them. So if you define blue compact dwarfs as dwarfs that have this blue core star formation activity, they could have. But in terms of other how we call it, like other properties, other constructional properties, I don't think so.
Another one. What is the statistical uncertainty or spread on the estimated average infall time?
It's pretty high for as you go deeper inside the cluster, it's pretty high. So here I'm showing you the infall time from the Pasquale method, so the average infall time, and on the third column is the uncertainty on the average infall time that you can get. And as you can see, as you go toward the zone 2 or 1, it becomes larger. So I know that there are studies now ongoing trying to minimize this uncertainty. But for our case, because we have the estimate from 2 different sources, so from this one and also from the simulations that I presented, so I'm not really worried about that. I think it's between 2 to 3.5 gigayears.
Great. There's one last one. Has the metallicity distance from the center relation you showed in the beginning been shown for other clusters besides the ones you've shown? Like
yes, yes. It's a well-known effect, not only for dwarfs, but also for massive galaxies, not very massive ones, because those are a different category. But between 10 to the 10 to the below 10 to the 10, this has been reported for different types of galaxies in different environments and clusters. Yes.
Have questions from the Zoom or YouTube? So I have one question that is, what surveys are you going to use in the near future and their methodologies to continue this interesting research on dwarf galaxies and their environment?
Well, most of the surveys currently available, not the upcoming ones, because upcoming ones are promising better data for low surface brightness galaxies and dwarf galaxies. But the current ones usually unfortunately, do not cover the mass range that we are looking at, or if they cover, they don't have the complete sample selection that we want. At this moment, I'm working with the cavity team, which is a survey on galaxies in the voids, in the cosmic void, so super undense regions of the cosmic web. And cavity is keeping me busy with the dwarfs, because the idea, one of the questions after this analysis, I will continue with the stellar population properties, because I mentioned they are fossil records of the galaxy evolution. But one of the questions is that where this tree processing took place. Do we really need a high density environment to kill star formation in dwarfs? Or could they quench themselves by themselves? Or in filaments, in galaxy groups, this can happen. So this is the question that I'm now focused on, and for this I'm collaborating with the cavity team, with the SDSS data, with the decals data. So these are the surveys that at the moment, because they provide a statistics, I'm currently working with them. Hopefully in future things will be better with the Euclid, with the Arachis. So let's hope for better future for dwarfs.
Okay. If we have no more questions, let's thank Bahar again for the interesting talk.
Thank you.
Thank you. We have a coffee break in the other room. And if you could fill in I've been sending around a Google Forms, because on the 7th of August, we're going to have short talk, and it would be very